Hello everyone, let's solve minimize maximum cost, maximum component cost. Let's understand the problem statement. You will be given n nodes labeled from 0 to n minus 1. You are also given two-dimensional array edges where edge of I represents the weight it takes to make a connection between u to v, node u to node v. And you are also given an integer k. You are allowed to remove any number of edges from the graph such that the resulting graph contains at most k connected components. The cost of the component defined as the maximum edge weight in that component. If the component doesn't have any edges, then we can return 0. The ask is we need to return minimum possible value of the maximum cost among all the components after removing of edges. Let's walk through an example. You will be given n equal to 5. That means there are nodes from 0 to n minus 1, which means 0 to 4. And all the nodes are connected through edges, and they are also given the cost it takes to connect between nodes. So if you see here, 0 to 1, the weight is 4, 1 to 3 weight is 2, and 1 to 2 weight is 3, and 3 to 4 weight is 6. So that's what this edges array representing. So we need to divide this graph into k connected components. So right now this graph is single connected component because all the nodes are connected. Now let's divide into two connected components because k equal 2. So we can remove the edge between 3 to 4. So once we remove that, the node 4 becomes independent component and other 4 nodes are connected as a single component. So among all these components, we need to return maximum edge. The max edge is 4, so that is what the expected output. So you might be thinking that this is also can be possible solution. We have 1 and we have 0 and we have 3 and 2 and 4 and we have 6 is the weight, 3 is the weight, 2 is the weight, 4 is the weight here. So let's remove edge between 0 to 1. Okay, so if I remove the edge between 0 to 1, so this is how my graph looks like. If you closely see, this is also two connected components. Now, among all these components, what is the maximum edge weight? So that is 6. So we need to actually return 6, but this is invalid. Why? Because we need to return minimum possible value of the maximum cost. So find out something which is minimum possible value of max cost. So here 4, 2, 3 all are valid, but we need to return minimum possible value of max cost, which is 4. So that's how it works. Hope you understand the problem statement. So let's move on. Let's say you have n equal to 5, k equal to 2, and these are the edges present in the graph. So you know, right, what is the thumb rule? So when you have a graph with n nodes, the graph has n nodes. If you want to make graph is fully connected, you just need n minus 1 edges, right? So you just need n minus 1 edges, right? So so let's see here. Let me take this example and draw a diagram. So this is what you have. So node 1 to 2, you have weight 3, and node 1 to 3 you have weight 2, and node 3 to 4 you have weight 6, and node 2 to 3 you have weight 5, and similarly node 0 to 4, 0 to 1 you have weight 4, and 2 to 4 you have weight 10. So if you closely see, this graph is fully connected, but you know that, right? If the n equal to 5, we just need 4 edges to make graph fully connected. But in this case, the graph is overloaded with extra edges, right? So we need to identify what are the possible edges can be removed. So obviously, we want to find out minimum value of maximum cost. Blindly, we can remove the edge which is having max weight, right? So to connect with 4, we have two edges. One is 3 to 4, other is 2 to 4. So by looking at this diagram, so obviously you can understand that the edge which is having maximum weight, which can be removed. Okay, so I can remove this edge. Okay, I can remove this one. And what is other one? So if you closely see total, we have six edges. If you closely see total, we have one, two, three, four, five, six. We have total six edges. We removed this one, and we need to find out what is the other one to be removed. I cannot remove this edge because if I remove this edge, this node 4 becomes independent. I cannot make my graph is fully connected. So obviously I need to remove either this edge or this edge. So which one can be to make a connection with 3, either I can remove edge 2, edge with weight 2 or edge with weight 5. One of the edge to be removed. So because these are the two duplicate edges, so obviously the edge which is having maximum weight can be ignored. That's why if you closely see, so this one can be ignored. Now if you understand, if you want to make, so once I remove these two edges, this is how the graph looks like. This is how the graph looks like. So let me draw that, or let me copy this. Okay, let me paste it here. Yeah. So once you remove it, this is how the graph looks like. So if you closely see, my graph has exactly, I have 5 nodes, but the graph has exactly 4 edges, and which is fully connected. If you closely see, the graph is fully connected, right? Now, how do you come up with a solution where you can remove invalid edges, right? So what are the things you need to consider? So point one is, if you want to construct a, first we'll construct a graph with valid edges, then we will think about how can I divide that graph into k connected components. So to do that, so we let's see what are the possible, so what are the things we should take care about it. Let me move little further. Okay, so what are the possible things we should take care? So one is we need to eliminate duplicate edges. Okay, that's it. So duplicate edges. Yes, we remove the duplicate edges because we remove this duplicate edge. Second one is we also need not to consider higher weight edges, right? So higher weight edges. So both the cases, whenever you are eliminating, you are eliminating the duplicate edge which is having higher weight. And when you reach n minus 1 edges, obviously you remove higher weight edges. So this is the concept of minimum spanning tree. So how do we come up with this solution? So let's see. Let's construct a graph which has exactly n minus 1 edges, and it has all the valid weights. So let's do that. So what can we do that? For sure, either of the case, we should avoid higher weight edges, right? So what can we do? Whatever edges we got, we will sort them based on the weight. So sort edges in ascending order based on weight. That's it. So let me do that. Let me sort edges in ascending order based on the weight. So this is the first one, so that I can take 1, 3, 2. Then this is the minimal later. This is the minimal, so that I can take 1, 2, 3. Then we have minimal edge is this one, so which has 2, 0, 1, 4. Then we have this one, which is 2, 3, 5. Then this one, 3, 4, 6. Then finally we have this one, so 2, 4, 10. Okay, so let's move on. Now let's construct a graph which has exactly n minus 1 edges. Okay, so to make your graph is fully connected, so I'll take one variable called a number of edges. So one variable called number of edges, which is initially 0. And also, when I'm constructing a graph, so generally how I am constructing, I am considering the graph with minimal weights, right? So I sorted already based on the minimal weight. I'm going to construct a fully connected graph. starting with minimal weight. So that's called minimums. That's a concept of minimum spanning tree. So I'll just write, I'll take a list, I'll track this information, what are the minimum weights I need to consider. I'll take a list of weight, weight, weight of minimum spanning trees. So I just take weights of minimum spanning tree. Let's say this graph can be called as minimum spanning tree, so which can be considered in the form of list. Let's move on. So first we have five nodes, right? So there are 0, 1, 2, 3, 4. So total we have five nodes starting from 0 to n minus 1. Initially there is no edge between any one of the nodes, so that number of edges are 0. So let's do that. First we'll consider this. Let's make a edge between 1, 2, 3. Okay, let's make a edge between 1, 2, 3. I can make because they are not connected. So as I make a edge between them, successfully made a edge between them, so that I can increase the number of edges by 1. So it becomes 1. And I'll also take that weight. So weight is 2. The weight will also be copied into my weights MST list. That's it. Now let's move further. We are trying to make a edge between node 1 to 2. Okay, let's make a edge between node 1 to 2. Yes, we can make it because it's a fresh edge, right? There is no connection between node 1 to 2, so that we will make a edge between them. So as we make a connection, so we can increase the number of edges by 1 and take the weight and also copy the weight into your list. Right. Now let's move further. 0 to 1. Can we make a edge between 0 to 1? Yes, because they are not connected. How do you know that two nodes are connected or not? So we will go with standard union find operations. So which always returns it always make a union between the nodes in constant time. So that we will get to know whether they are connected or not. If they are not connected, we'll just make a connection between them. As we make a connection between them, we can increase the number of edges by 1, and whatever weight we take it, so we are also copy that weight into weights minimum spanning tree. Now this is where the critical point. Now let's see, we are having 2 to 3. So can we make a connection between 2 to 3? If you closely see, if you closely see 2 to 3, right? So node 2 and 3 are already connected. Node 2 and 3 are already connected, which can be reached node 3 through node 1. So they are already connected, so we don't need to make duplicate edge. That's why we can simply ignore this. If the nodes are already connected, so we can simply ignore this. So we don't want to make duplicate edges. So obviously, what do you see? Node 2 and 3 are already connected, so that we don't consider this edge. That's how you make that's how you make your graph as minimum spanning tree. So you are constructing a graph with valid number of minimum edges. Now let's say this is how it is. So now we are moving on to 3 4. So node 3 to 4, can we make a edge between node 3 to 4? Definitely, because they are not connected. So as you make a edge between them, so that you increase the number of edges by 1, it becomes 4, and the weight is 6. You copy the weight into weight MST. Now let's understand number of edges. What is the number of edges? 4, which is equal to n minus 1. So which is equal to n minus 1. It means you constructed a graph with n minus 1 edges, so that you have a fully connected graph, so that we don't need to proceed further. Whatever edges you could see after that, right, all the edges can be ignored. So whatever edges you could see after that, all the edges can be ignored. So you already constructed a valid minimum spanning tree graph. That's it. So this is what we have. So we already constructed it. Now it's time for us to divide this graph into expected components. So we need to divide this graph into two components, two connected components, as k equal to. So let's see here, k is equal to, right? Then in order to divide this graph into two connected components, how many edges to be eliminated? So that's the point. So how many edges to be eliminated? To be removed. You can say how many edges to be removed. Simple, it is k minus 1. So it means here k equal to, right? So k minus 1 becomes 1. So if you remove one edge, that's it. This graph becomes two connected components. What is the edge to be removed? Obviously, we need to return minimum value of the max count, max cost, right? Definitely, we need to remove the weight, the edge which is having max weight. So obviously, we need to remove this edge. So once we remove this edge, this is how it looks. So let me remove that. So once I remove this edge, okay, so I remove this edge. So once we remove this edge, if you closely see, you have two connected components. So this is one component and this is another component, out of which we need to return max cost, which is 4. But how do you figure that out, right? How do you figure that out? You don't have to you don't have to traverse the complete graph and identify it. So you don't have to do that. For that purpose only, we maintain a weight MST. The weight MST graph list will always have the weights in ascending order. Why? Because whatever weights you copy here, right, all the weights are copied from the edges list. All the edges were already sorted based on ascending order, in ascending order based on the weight. So that obviously weight MST will have what? The weights of each edge in ascending order. So it means 6 is the weight of edge 4, 4 is the weight of edge 3, 3 is the weight of edge 2, and 2 is weight of edge 1. So you already know the edges, right? So when you have k equal to 2, if you want to make uh, if you want to make this graph is k connected components, we need to remove k minus 1 edges. It means we just, in this case, k equal to, so that we need to remove one edge. What is that edge which is having maximum cost? So in the MST, you already have the 6, right? So the last one, so we just need to remove the last one. And after that, whatever value you have before that, that is your answer, right? So that is your answer. So once we remove this, so this is our answer. That's it. So simple. So you simply return 4, right? You get it, right? You get it. I think I hope you get this. Now what is the time complexity here? So can you tell me the time complexity here? The time complexity, what are we doing? So we are sorting the edges. Let's say you have edge E and we are sorting the edges. So it will take E log E. So we go of E log E plus, what are we trying to do? We are trying to construct a graph, right? So with E edges, and generally we use union find operation. The union find operation on an average, which is going to take constant time. So at how many edges you have doesn't matter. Every edge is going to take constant time, so that the time complexity will be big O of E log E plus E. That's it. So it said the time complexity is big O of E log E plus E. And what is the space complexity here? So what is the space complexity here? The space complexity is, we are using union find, so which is going to take a root array or parent array in order to make a connections between the nodes. So obviously the size of that root array is equivalent to given n, so that the space complexity is big O of n. And let me walk through the use cases. So let's say here we already know that. So we constructed a weighted MST graph, which is returning the values as 2 3 4 6. Okay, so 2 3 4 6, and we want to divide this graph k equal to, so you already know that you just need to eliminate k minus 1 edges, right? So that's how it works. You just need to eliminate k minus 1 edges, so which is one edge. So one way to find it, to identify the answer is, you start from the right and just move towards left. So I want to eliminate one edge, so that I need to skip the one, so the remaining one is going to be the answer. So this is one simplest way to find out the answer. Other way is, if you see here MST weight, so MST weight, which is 4, right? And as the index number starting from 1, so you can find out a formula simply. So 4 minus 1, index number starting from 1, and minus k minus 1. So if you closely see, which is going to be 4 minus 1 minus k means 2 plus 1. So k value is 2, right? So 2, so obviously which is going to be 2. So this also gives the exact index. If you closely see, this is a list, right? So you can represent as 0, 1, 2, 3, so that you can directly return it. So I can call it as, if you frame it as a formula, so assume that the size of this minimum spanning tree equal to n, then you can take n minus 1 minus k minus 1, so which is going to be n minus 1 minus k plus 1, so which is going to be n minus k. So you can directly get n minus k. So in this case, if you see n equal to 4, right, because the element size is 4, and k equal to 2, so k equal to, so which is going to be 2. So at index 2, whatever value you have, that is your answer. So this is one of the easiest way to find out. So one way is you can traverse from left to right, sorry, right to left, and eliminate k minus 1 edges, and k minus 2 value is going to be your answer. So that's the simplest way. But if you want to find out through formula, so you can simply get through n minus k. Okay, right. Now let me cover one more edge case. Let's say you have n equal to 5 and k equal to 5. So it means, what does it mean? Your k and n both are same. So what does it mean? So you have five components, five nodes, sorry, five nodes in your graph. So starting from 0 to 4, and you want to divide that into five components. It means, what does it mean? So you don't have any edge between the components. So it means there is no edge established between the components, so that in that case the number of component size is equivalent to n. So it means whenever your k value is greater than or equal to n, so you can blindly return 0. So it means when k is greater than or equal to n, so you cannot make edge between the nodes. So it's simply you can return 0. Hope you understand the algorithm. So let me go and submit the code. Yeah. So the best way, first you can define the union find. So I hope you already have idea on union find. If you don't have knowledge on it, please check out my video. I already made a video on union find, so please check out it, so things will be clarified. So simple. So I'm just trying to create a root array with the given n, and I'm just trying to starting from 0 less than n plus plus. So initially every vertex root is itself, so that I'll just say root of b equal to b. Simple. It's a simple way of constructing union find root array. Then I'll just have uh, find method, so which is going to return the root of given node. I'll just say if the node and its value is not equal, then I can just move on to its parent. So you can just say root of x equal to find of root of x. Hope you are getting this. This is path compression. So this definitely makes us our find method more efficient, and on an average it leads to the constant time. Okay, so hope you get it. And you can also use union by rank here, but in order to avoid the complexity, I'm just skipping that. And I want to know, I'm also using union methods, which is making a connection between the node x and node y. So first what we do, we will find out the root of the x, so you can call find of x, and root y, so you can call find of y. And if both roots are equal, it means they are already connected. So when they are already connected, so we should return false. So we need to ignore duplicate edges. Otherwise, you can make one of the, so I'm just using root y, root I am making as root x, then just return true. That's it. So even the union and find method will return, on an average, it will be constant time. Let's move on. Now, what is our job now? First, we need to sort edges based on weight in ascending order. Perfect. So prior to that, so let me handle the edge case. So whenever your k is greater than or equal to n, it means you don't need to form. There won't be any edge between the nodes, so you simply return 0. Otherwise, then we will sort edges based on weight in ascending order. So let me do that. Um, so let me do that. You can simply use arrays dot sort, and this is our edges. Take h1, h2, then integer dot compare of h1 of 2. At index 2 we have weight, so h2 of 2. That's it. So it will sort the edges in ascending order based on weight. Then what is our job? We will initially take number of edges, which is 0, and we are also taking a list of integers. So this is our weighted MST. So you can call it as new array list, because we need to track all the weights such that we can return the valid answer. That's it. Then we are going to create a union find, and this is our union find of given n. Then we will move on. So this is our edge from edges, and take node u, which is present in edge 0, and node v, which present in edge 1, and we are also considering weight, which is present in edge 2. Perfect. So now what is our job? We will see, can we make a connection between node u and v? So we can do that through union find union method. It will just make a connection between u and v. So if they are able to connect, then it's time for us to increment this number of edges. You are able to establish a edge between node u to v. Then whatever weight you took it, right? So just add it to the weighted MST, so which will be useful for us to return the result. Then we will see if our number of edges, right? If our number of edges which is equal to n minus 1, so it means you constructed a um, fully connected graph. So just simply to break. That's it. So finally, what you do, you just need to return k minus 1 edges to be eliminated from this weighted MST. So either you can do traversal, or I can just do this weighted MST size, right? So let's take size equal weighted MST size. So I can just take this size minus k will hold the same value. That's it. So hope you understand the code. Let me run. Let me submit. That's it. Hope you like the explanation. Please do subscribe and share. I'll give you one more thing. So do you really needed to maintain this weighted MST? You know when to stop, right? I'm giving to I'm giving. You can try yourself. Give a thought on it. So you can eliminate this weighted graph. Still, you can able to return the valid result. Give a thought it. If you couldn't able to understand, please let me know through comments. I will provide the solution. That's it. So thanks for your time. See you next time.